Hi, in this video we are going to talk about some instrumental analytical methods, and in this video we will be focusing on the calorimetry as well as the infrared spectroscopy. For mass spectrometry we will discuss it perhaps in another video. So first of all, this part belongs to the topic analytical chemistry. So if you have the notes, it is going to be page 42. You can also find an excerpt of my notes from the description below the video, and make sure you have prepared this. Now, before we start, in fact, so far when we are talking about analytical chemistry, if you kind of recap your memory, at the first place we talk about some chemical tests to test for ions or gases, gaseous molecules, or even some functional groups, right? So what we are trying to do here is to do something called qualitative analysis. So basically finding what it is, And we also talk about titration techniques, which allow us to find out how much a particular sample or a particular chemical in a sample, all right? So for this one, we call it quantitative analysis, finding how much it is. Now, so we kind of learned some technique to find out what it is and how much it is, right? Now, for all these chemical tests or methods, we call them wet chemistry, because they are dealing with chemicals, and we are making use of some kind of reactions to find out what it is and how much they are, okay? However, in this part, instrumental analysis, this is not considered as wet chemistry because first of all, we are relying on some kind of instrument, and instead of using chemicals to actually carry out the analysis, also for these methods, we are relying on some electromagnetic waves to find out what it is and how much they are. Except mass spectrometry, while electromagnetic wave is involved, but instead of using the electromagnetic wave to directly interact with the chemicals, well, anyway, the working principle is a little bit different than the two before, okay? Now for these two, we are making use of some electromagnetic radiation, visible light for calorimetry, and obviously infrared for infrared spectroscopy. We're making use of the interaction between the substance as well as these EM waves to find out what it is and how much they are, okay? So that's the idea. Okay, so let's get into it. Let's talk about the calorimetry. So obviously, calorimetry is used to find out how much of a particular substance using or making use of its color. So if we have a sample, and we're talking about aqueous sample, not a solid, not a gas, okay, an aqueous sample, and one of the solutes is colored, okay? So for example, if you learn about, for example, Fe2 plus AQ, you know that it is pale green in color. So this is an example of aqueous sample, and one of the solute is colored, okay? And we know that the concentration of the solute is directly proportional to the color intensity, right? That makes sense. So the more concentrated the Fe2 plus is, the more green it is, or the intensity of the pale green color increases, and that makes sense. And if you see it being a green color or very green color, that means they must have absorbed some of the light, and the greener it is, the more light that it absorbs. But the question is, what particular color will a green sample absorb the most? Actually, we can make use of the color wheels to predict what will be the predominant color being absorbed by this sample. So here, this is basically like a rainbow, the color, red, orange, yellow, green, blue, purple, and they form a wheel, so we call it a color wheel. And let's just say our sample here is green in color, right? So we are trying to look at is opposite color or the complementary color. So the opposite color or the complementary color of green is obviously red, also perhaps purple. So in fact, if something that is green in color, just like this sample, it will absorb predominantly red and purple. And obviously, it should not absorb much of its own color, right? That makes sense because this is the reason why we see the green color from a green substance, because it does not absorb green. Instead, they reflect the green towards our eyes, and that's why we can see it. Okay, so you can easily tell if I have if I have a sample which is green in color here, okay, and if you have red light going through it, and if you have, let's just say, blue light going through it, and if you have green light, okay, going through it. So, like I said, the green will mainly absorb the red and the purple or blue, right? So, after the red light passes through the sample, you should see fewer, okay, red light that can actually pass through. Similar idea for blue, right? You should see lower intensity or decreased intensity of blue. However, for the green, it does not absorb much, right? So you can still see the majority of the green light still there. So this is the reason why. So the red and the blue are absorbed, but the green, not much. Okay? So that's the idea. Down here, we say that if the concentration of solute is higher, the color intensity is obviously higher. And when the solute concentration is higher, the absorbance will also be higher. Now for absorbance, this is basically how much of a particular light is being absorbed. Alright? So if you have a higher concentration, it has a higher color intensity, it will absorb more light. Okay? So the absorbance tells you how much light is being absorbed by the sample. Okay? Now here we are introducing something called a calorimeter. So a calorimeter is an apparatus used to determine the concentration of solute based on its absorbance. Okay, we are measuring the absorbance. Okay, like I said, the absorbance is directly proportional to the concentration of solute, right? So we're making use of this relationship. So this is how it looks like. There are a couple of parts. So the first part is a light source. Now the light source provides a linear white light. Okay. Of course, if you have a light source that is already able to provide a linear light, then that would be fine. But if you do not have it, a very primitive way of doing this is, let's say you have a light bulb, okay, and then basically you put it into a box, but you poke a hole here, right? And let's just say this is a black box, and you poke a hole here. So when they light up, then obviously you will have a linear white light source, okay? But most of the time when we are using calorimeter, we will have a linear white light source, okay? And some of them even allows you to choose the color, okay, already inside the light source. Now let's just say this one provide a white light, but we are not using the white light. Instead, we are choosing a particular color using something called a filter, or sometimes we call it monochrometer. Now this one is used to select a monochromic light. Now what do you mean by monochromic light? Mono means one, right? One. And chromic means color. Okay? Chromic means color. So that means a light with a single color. Alright? And the reason why we are choosing a particular color is because we try to choose the complementary color of the sample, so that the result will be more obvious, and we will not have other color that complicates the result or complicates the spectrum. Okay, so we choose a monochromic light, which is complementary color of the sample color. So remember, complementary color again is determined by the color wheel. Okay, so again, if this one is now you see over here. I use a blue color to represent the monochromatic light. So can you guess what is the color of the sample? Now it is just the reverse thinking. So if we are choosing a blue, then the opposite color or the complementary color of blue is orange, meaning that our sample is actually orange in color. Okay, so you can think about it as a orange. Okay. Okay, running out of ink, but okay, this is the orange over here. Okay. So that's why we choose the blue. So actually the filter will also be blue in color. Okay. Now, here we have something called a cuvette. So a cuvette is actually a small little container, like a square, a rectangular, cylindrical shape, made by silica glass, and they are transparent, colorless glass containing the sample, and usually it is 1 cm wide and length, because it's a square actually, so it's 1 cm on each side. Okay, for some reason. So it is more like a standard size. And lastly, we have a detector, which is basically to detect how much monochromatic light are able to pass through. Okay, so obviously you will expect to see a decreased light intensity because of the part of the light being absorbed. So basically they are comparing the amount of light that is direct to the sample before and after it passes through the sample, and the difference will be allowing us to find out the absorbance. Okay. Now, of course, the actual design is more complicated. The actual design will actually have another control setup, which having an empty cuvette, and they try to measure how much the light absorbed by the cuvette, and also kind of scattered it as it travels along the distance. So imagine it has another setup right here where it has an empty cuvette. So they measure the amount of light reaching the detector, and then also measure the amount of light reached at this detector, and the difference between the two setups will be telling you about the absorbance. Okay. Even though you do not have two setups, but at least you can put an empty cuvette inside for calibration. So you take a blank record or blank data, and then you actually carry out the analysis, and the computer itself is allowing you, or you can do it manually. Okay, you are able to find out the actual absorbance. Okay, so that's the idea. And the data collected right here is used to generate an absorbance concentration graph by a computer. So which is down here. You see absorbance concentration graph. Okay, this one. So it should be having a directly proportional relationship, right? Should be a straight line. Okay. All right. So now you may ask a question. Okay. So now obviously I understand that with a higher absorbance, with a higher concentration of solute, it will have a higher absorbance. But like I previously said, we are trying to carry out quantitative analysis, right? So how much? Now, even though I know the absorbance, how can I translate it into concentration, right? How can I translate it into concentration? So imagine you just have a sample, you load it into a calorimeter, and then at the end they give you an absorbance. Let's just say absorbance is 100. So what does this 100 means? How can we translate it back to the concentration? So that's why actually before we carry out the analysis with our sample, we need to do one important step. We call it calibration. Okay, calibration. Okay, so how do we do a calibration? Is in fact we use several standard solute solution. Now standard solute solution means they have known concentrations. Okay, concentrations. Okay, so let's just say if you go back to this example, if you want to really analyze iron 2 iron solution, then before you load your unknown sample, you should prepare yourself some standard solution of Fe2+. You got some like 1M, 2M, 3M, etc. And then you actually load it into the calorimeter, and you find the absorbance data. You find the absorbance data from these standard solutions. Okay? And actually you need to use at least two, because to create a straight line you need at least 2 data points. But of course the more the merrier. So actually this one is a calibration curve. This is a calibration curve. Okay? So all this across here is basically data point. It's basically standard solution, probably 100, 200, 400, 500, etc. And then we load it into a calorimeter for the calibration. So we establish this curve, allowing us to later on translate the absorbance back to concentration. Okay? So this is the idea. So you see here, suppose we have an unknown sample that gives an absorbance of 0.6. Using the calibration curve, you know that it is actually 300 concentration. Okay? So this is how it works. Now you may ask, what do you mean by 300 concentrations? Actually, the unit here is ppm, parts per million. Now what do you mean by ppm? So over here on the right hand side, so here, ppm is a common unit to express the concentration of a very dilute sample. Now, this is one of the advantage or strengths of calorimetry or the instrumental analysis, because if our sample is very, very diluted, so diluted to the point where titration is not feasible, then we need to use the instrumental analytical method. So usually, if we are going to use these calorimetry technique, we are dealing with solutions that are very diluted. Okay? So when it comes to very diluted sample, instead of using the mole per dm cube, sometimes we use the unit called ppm. The ppm stands for parts per million. Here, parts per million, which is calculated as follows. So C ppm, the concentration in terms of ppm, equals to the mass of solute over mass of solvent times 10 to the power 6. So this one corresponds to 1 million. 1 million. Okay? So basically we want to find out how many parts of this solute per 1 million particles, solvent particles. Okay? So that's why we multiply by a huge number. Okay? So you see, calorimetry is a very useful technique to determine very dilute sample with high accuracy, which will otherwise be very challenging. Okay? So this is the strength or advantage of using this technique. Okay? Okay, so let's have a look at this practice question. So first of all, you are given with a calibration curve and absorbance versus the concentration times 10 to the power negative 5 mole per dm cube, and we are trying to study the concentration of copper 2 plus ion. Okay, copper 2 plus ion. Now, part A, outline how a calibration curve is produced. So 2 marks. So first of all, the key thing is you need to mention about using several standard solution of copper 2 plus. Okay, and then we need to load it into the calorimeter, find the corresponding absorbance, and then plot a graph. So actually it is on this page right here. Okay, so here it is the practice question. Okay, A, right? So I do not copy over here. Now, part B, in the calorimetry experiment, an orange filter is used. Explain why. So this one was actually asked in the DSE before. The reason why we use an orange filter is because Cu2 plus Aq is pale blue in color. Okay? and orange is the complementary color of pale blue, which is our target solute. Okay? So you need to mention about the color of Cu2 plus, as well as orange being the complementary color. Okay? Alright, and C, a sample of copper 2 sulfate is first diluted 1,000 times, and then we carry out the calorimetry, and we find out the absorbance being 0.7. So calculate the concentration of the undiluted sample. So actually it is quite easy. So first of all, from the calibration curve here, so 0.7 is over here. So if you extend this part and you try to find the intersect, so roughly, probably you'll find, I guess 36, right? 36 over here. So from the calibration curve, okay, the concentration of diluted sample is 36 times 10 to the power negative 5 mole per dm cube, right? So the undiluted sample, undiluted Cu2 plus AQ's concentration is 36 times 10 to the power negative 5 times 1,000 times, because it has been diluted at the first place. So it's going to be 3.6 times 10 to the power negative 2, I guess. Okay, just to be safe, 36 times 10 to the power negative 5 times 1,000. Oh, okay, so we can actually put down this one. Okay, so that's the idea. Okay, now before we move on, I just want to also point out one concept over here. So, previously we talked about if we have a sample, let's just say it is a green in color. So you know that the opposite color is probably red, right? So if you have a red light that is passing through the sample, you will have diminished intensity of light passing out, right? So, and then we have a detector over here. We have a detector over here, which is detecting the amount of light that is left after going through the sample, right? Now, actually, the detector is measuring the intensity of light that is able to pass through the sample. So actually, this intensity of light that is able to detect it by the detector is called transmittance. Okay, transmittance. Okay, transmittance. Okay, so transmittance means basically how much light that can pass through. Okay, so you can tell when the concentration, if the concentration of the solute is high, then the transmittance would be high or low? Would be low. Okay? That makes sense, because if you have more solutes there, it will absorb more light, so less light will be able to pass through the sample and ending up at the detector. So the transmittance will be lower when you have a higher concentration of solute. Okay? So less amount of light can actually pass through it. That makes sense. So, but you also know that if the solute's concentration is very low, then if you talk about the absorbance, right? Absorbance, this is what we have been talking about. The absorbance will be high. So you kind of know the relationship between the two terms, absorbance and transmittance. Absorbance. Okay, how much light is being absorbed? So that makes sense. If you have more light being absorbed, you have less light able to transmit across the sample, right? That makes a lot of sense. So think about it. If you are talking about a graph, okay? If you are talking about a graph and you have the concentration of solutes at the x-axis, so previously from the calibration curve here, you know that. Sorry, I make a mistake here. We are talking about going up as well. Sorry, going up as well. So with a higher solute concentration, the absorbance will be higher. So of course, when the concentration of solute is increasing, then the absorbance will also increase, right? But if you try to talk about the transmittance, then that will be the exact opposite, right? That would be the exact opposite. So it would be like this, right? This is the transmittance, right? Okay, so that one tells you about the relationship between the two terms when we talk about the solute concentration. Okay, so at least I want you to know this term, because later on when we talk about infrared, they actually talk about transmittance. Okay, so let's move on to the next page. Now, infrared. Infrared spectroscopy. So, in fact, the idea of infrared spectroscopy is quite similar to calorimetry. So again, we are providing an electromagnetic wave to our sample, and we try to look at how much of a particular light is being absorbed, and therefore allowing us to from the absorbance or transmittance, we are able to tell how much light is being absorbed. Okay, but the difference is that in this case, we are not usually using IR for quantitative analysis. In fact, IR is mostly used for qualitative analysis. So instead of finding how much of a sample, we want to find out what is the sample. Okay. Now, in this case, in IR, in fact, we are trying to find out what functional group or what kind of structural features of a particular organic sample. Okay? So, we are trying to find out what instead of how much. Okay? Now, so the idea is a little bit different. Instead of using one particular wavelength of light, and to see how much it is being absorbed, we are now providing a collection of wavelengths of radiation, and we want to find out which particular wavelength of light is being absorbed by our sample. And the wavelength of light being absorbed can be inferred or can be interpreted into some structural features of a compound. So the idea is quite different than calorimetry. Although the way we carry out is very similar, but the concept is a little bit different. Okay? Now, let's have a look at some kind of basic principle. Now, we say that in organic compound, they are all molecules and covalent molecules, so they have different covalent bonds, and different covalent bonds are able to absorb a particular wavelength of light in order to carry out something called bond vibration. And this particular light is within the infrared region. Okay? The very simple idea is the bond vibration requires a certain energy, and this particular energy turns out fits within the infrared region. So not very high energy EM wave. Is actually weaker than visible light, but this is the wavelength of light or the energy of the light where bond vibration requires. So it happens to be like this. Okay? Now for bond vibration, the detail or the mechanism of bond vibration is not required in DSE. If you are interested, you can ask me later about how the bond can actually vibrate and what do you mean by infrared active, what do you mean by infrared inactive. If you are interested, you can ask me, but it's out of the scope of DSE. But anyway, so you have an idea that a different covalent bond absorb different wavelengths of infrared light for bond vibration. Okay? So if we provide a collection of wavelengths of infrared to our sample, we are able to find out which particular wavelength is being absorbed. Okay, so if we find out some absorbance of a certain wavelength of IR, it is allowing us to determine what kind of covalent bond exists in the compound, which then tell us what possible functional groups are there. Okay, so like I said, this IR technique, IR spectroscopy, the main function is to find out what functional group or what functional groups are there in an organic compound. Okay? Now, let's look at a case study here, very important case study. Now, this is an infrared spectrum of a compound called 2-propenoic acid. The structure is given here. Okay, now whenever we look at a spectrum, make sure we know the y-intercept and x-intercept. Y-axis and x-axis. Now, I would say, personally, infrared spectrum is quite weird. It's quite weird. I will explain why right now. So first of all, you look at the y-axis. Instead of using absorbance, they actually use transmittance. So remember what I mentioned about the difference between absorbance and transmittance, right? So the lower the transmittance, the higher the solute concentration, all right? So in this case, the lower the transmittance actually tells you that that wavelength of light is being absorbed, okay? So that's why when we look at this graph, we are looking at the peaks, the so-called peaks, okay? You know, peaks supposed to be the top of a mountain, right? But here, the so-called peaks is talking about those points where the transmittance is very low. So the so-called peaks are actually talking about this, it's talking about this, it's talking about this, okay? These are what we call the peaks, but which is pointing downward, okay? So it's quite weird. So this is weird point number one. Okay, they use transmittance instead of absorbance. Now the weird point number two is you look at the x-axis. So this one we call it wave number. Wave number. Now what do you mean by wave number? So if you're not studying physics, now wave number is actually the reciprocal of wavelength. So you should know that. So let me put it down here. Wave number actually equals to 1 over wavelength. Okay? So it's the reciprocal. Okay? So that means they are in an inverse proportional relationship. Okay? Now I try to substantiate a little bit about the physics. So you know that down here, if the wave number, okay, if you have a high wave number, for instance, you know that the wavelength should be shorter, right? Because of the inverse proportional relationship. Okay, the larger of this number, the smaller of this number, right? And if you learn about it in perhaps Form 3 physics, you learn about V equals to F lambda, right? And V stands for frequency, right? So you can tell if the wavelength is shorter, okay, so the frequency should be, V stands for velocity of light, which is the speed of light. So this is frequency, this is the wavelength. So and they are actually in an inverse proportional relationship. So the shorter the wavelength, the higher the frequency. Okay, and I'm not sure, I think you should know it. The higher the frequency of light, actually the energy of the light is also higher, okay, a higher energy of light. So I just want to substantiate with you with this very basic physics idea, okay? Now, going back to the top here. Okay, so first the x-axis, the wave number, okay, and here, so that's why I said wave number is directly proportional to the frequency of light, okay, as I have derived down there. And also pay attention, usually for a graph, the zero should be here, and then the number going larger towards the right-hand side. But you can tell it is a different story. The larger number is actually on the left. So that's why this is the weird point number 2 for infrared. So make sure you adapt to it, okay? Make sure you adapt to this kind of notation. And probably you need to know the axis label, okay? All right, so okay, so point number 3 here, which is talking about how do we interpret the graph. So actually, when we look at the infrared spectrum, we are focusing on the peaks, okay? Like I said, like I circled it here. So because the peaks tells you what particular wave number of infrared light being absorbed, right? So we try to focus on the peaks. But you may ask, sir, there are so many peaks around. Do I have to know every single one of these? To be honest, no. To be honest, no. In fact, for infrared, we are mostly focusing on 3 particular wave number or 4, okay? So let's have a look at what I have circled here. So when you look at this one, okay, when you look at this one, so you see there is quite a broad peak, sorry, let's move on. Let's look at this one first. Now you see there is a very sharp, intense peak at a wave number of around, if you're over here, you see this was 1650 cm to the power -1, right? 1650 around, okay? So this one, if you check the table on the right hand side, you see this one should be given in your DSE exam. So if you see a 1650, a 1650, so that is actually this one. Okay, that belongs to this range, and that tells you the presence of CC double bond in your organic compound. Now this one is a very important information because you know that it should have an alkene. It should have a CC double bond and maybe an alkenyl group. Maybe it is an alkene, right? So from here, our assignment or our deduction is that there would be a CC double bond. And do we have it? Yes, we surely have it. Okay, the CC double bond here. Okay. Now, the next thing we try to look at is this one. Okay. You see, this one we have another sharp peak almost to the bottom. Okay, and this one we are talking about. Okay, 1,700. Okay, cm to the power -1. Okay, so 1,700. If you check out the range over here, it's actually talking about this one. Right? So that one is corresponding to the presence of CO double bond, a carbonyl group. Okay? So this one, we know that it is CO double bond. Okay? So, which is also present here. Okay? Alright? And then lastly, as you can tell, this one, this very broad peak over here. So this one, we are usually talking about a kind of range between 2,500 to 3,500. Okay, so we have a wider range. If you check out the table on the right hand side, for this range, it could either be this one, 2,500 to 3,300, or this one, 3,200 to 3,600. Now, in fact, even though they have separated into 2 areas, but usually we cannot be so sure which one is which. So for me, my suggestion is these 2. We collectively regard it as 2,500 to 3,500. Okay? So because they are referring to actually the same bond, OH, right? So usually I will suggest my student to look at a broader range to see if there is a peak there. And very importantly, this peak is what we call a broad peak. This is the only peak that is very broad. Now, broad peak means over here, they kind of occupy a huge area across on the spectrum. Okay, you see all these are what we call sharp peak, very sharp. But this one is obviously very broad, or sometimes we call it fat peak, very fat. Okay, so this one is corresponding to the OH over here. Okay, so in fact, this is the key peaks or key region of wave numbers that we have to pay attention to. Because if you check, alkyne is very rare. Of course, that may be asked in the DSE, but very unlikely. Nitrile as well. And then moving on, CH. Now CH, actually if you look at the wave number range, yes, we do have CH, right, which is over here, right? Actually, it's over here. This is the CH bond, okay, the sharp peak. But, you know, because the majority of the peak is kind of masked by the broad peak over here, so we only see a very tiny little dip. But the problem is, the question is it useful? Is it useful? To be honest, which organic compound does not have a CH, right? Most of the organic compound will have a CH. And, you know, the presence of CH does not really helpful for our deduction, right? It's not even a functional group. So like I said, most of the time we are looking at either 3 wave number range or maybe 4, including this one. Okay? Now, one more, the NH. Now, NH here, it has also a particular range, but NH here, actually there is a special feature. We call it exists as a twin peak. So in fact it is like this. Over here they got like a sharp peak over here, another sharp peak over here, and so on and so forth. Okay, so here, over here, this is what we call the twin peak, which is for the amine. Okay, amine. Okay, but it is quite rare to see that twin peak. Okay, which is corresponding to this one. Okay. That means if you see a twin peak over there, that has to be amine. It has to be amine. But very rare, to be honest, very rare. Most of the time it is these 3. Okay, so pay extra attention to this. Okay. All right. So down here, so this is what the point number 3 is talking about. The peaks, also known as the dip or the bands. The dip is because it is actually we are looking at the lowest point on the graph rather than the highest point. So that's why it's called dips. Showing which wave number of IR being absorbed the most, indicating the presence of a certain covalent bond or functional group. Okay. You see, most of the information is obtained from the range of 1,500 to 4,000. So most of the time we are focusing on this part. Okay, this part. Okay. So what about this part? Now this part, you see the peaks are actually quite populated. There are quite a lot of peaks here, quite complicated. For that part, it is not for us to do the analysis. Actually, this part is for the machine, for computer to do the analysis, because that part is very complex. Okay, so that part usually we call it the fingerprint region. So you know every person has his own unique fingerprint. So the idea is, in fact, this part allows us to find out what the sample is. What the sample is. So in reality, you know, we have a lot of literature value. So scientists, chemists, they find different kind of organic compound. They load it into an infrared spectrometer, and they try to generate the infrared spectrum for each organic compound. So if we have an unknown compound and we load it into the IR spectrometer, after we generate the spectrum, we can compare with our data bank, compare with the literature value to see which one fits the most. And mostly the computer will compare the spectra using the fingerprint region. Okay, because every organic compound should have its own unique fingerprint region. Okay, So this one, instead of indicating the presence of a certain functional group, the fingerprint region mainly serves as an identification of a certain organic compound. Okay, so that's the idea. Now on the right hand side here, this is actually what I have talked about, but this one tells you how we actually describe or to put down the assignment. So basically, how do we present our findings, or how do we present our analysis of the infrared spectrum? So over here, you see, when we are describing a certain peak, we need to describe the shape of the peak, where do you find it, and also what kind of inference or what kind of prediction, okay, from this particular peak. So here you see a broad peak across a range of 2,500 to 3,400 indicates the presence of OH bond. Now the OH bond suggests the presence of a hydroxyl group or a carboxyl group. Okay, so it tells you about the functional group. Here, a sharp peak at 1,700 indicates the presence of a CO double bond, so which suggests the presence of a carbonyl group, probably an aldehyde, ketone, ester, carboxyl group. Okay. 1,650 tells you about CC double bond, so suggesting the presence of a CC double bond. Okay. And the CH bond here is not very important, but I just also put down here. So this is how it works. So listen up. Whenever we look at the infrared spectrum, don't panic. Very simple. Just put extra focus on these three regions, and I think you should be able to solve like 90% of the situations. So let's have a look at a practice question here. My suggestion is you try to pause the video and try to work on these practice questions, or at least the first two. Okay, at least the first two infrared. First two questions. Okay. Now I assume you have already done it. So this one, identify the bond responsible for each absorption. Label 1, 2, 3. You can always refer back to this table, because this one should be given in DSE. You are not required to memorize all these numbers. Okay, so let's do something easier. Number 3 here. Number 3, you see, it is actually 1,700. So 1,700 is corresponding to the C double bond O. Okay, just put down the bond, right? Identify the bond. Okay. Now, 1 here. Okay, you may see it's kind of like 2,950, right? So, is it going to be the CH bond? Is it going to be the CH bond? In fact, it is not the case, because this one is pointing the whole area, the broad peak. So this one is more likely to be OH. Okay. Now, what about this particular sharp peak? Okay, sharp peak at around 2,700. So you may flip over this table. You see, sir, 2,700. We don't have it, right? Is it going to be the OH? Is it going to be the OH? Not the case, because for OH we have already indicated, and it should be a broad peak rather than a sharp peak. So in this case, actually, the most relevant bond would be the CH. Okay, CH. So this one is actually corresponding to the CH bond. Okay. Now, so sometimes the actual wave number may be fall outside the given range. So you need to adapt to it. Now, question 2 here, more complicated. So suggest 3 characteristic peaks that I expect to see in an infrared spectrum. State the covalent bond corresponding to each peak. So for this one, I'm trying to ask you to use what I did here. Okay, try to write down the assignment using this kind of sentence pattern. Okay, so actually not very difficult. So first of all, maybe I will talk about the CC double bond over here. So I would say, okay, 1, a sharp peak at 1650 cm negative 1, okay, suggests the presence of C double bond, okay, just like that. And then you can mention about the OH, okay, so again, for this time it should be a broad peak, okay, at the range of, so because this is an OH, so OH you should be having, I think, the range of this one, because this one is corresponding to the alcohols, the phenols, right? So it should be here, 3230. You can just copy from here if you're not sure. What was that? 50. Okay, so suggest the presence of OH. Okay, and lastly, the only one that you can talk about is the CH bond, the CH bond over here, the CH bond over here, or maybe here, or maybe here. Not very meaningful, but this is the only peak that we can mention, a sharp peak at 2950 cm negative 1 suggests the presence of CH bond. Okay? So this is how we do the assignment, how we describe, okay? Okay. So shouldn't be a problem. Now let's look at the next page. So this is the last practice question. So here a student mixed up infrared spectra of ethanol, ethanol, and ethanoic acid. So you are trying to determine which one is which and try to give your reasoning. All right. So again, pause the video and try to work it out. Okay. Now, suppose you have done it. So the first thing you're going to do is you need to know the structure of ethanol, ethanol, and ethanoic acid, right? So, of course, ethanol is like this. Okay, ethanol with the OH here. Ethanol is with a CO double bond, and ethanoic acid would be OH, right? So, of course, you can tell the ethanol will only have the OH, and the aldehyde, the ethanol, will only have the CO double bond. So, we are basically making use of these two structural features to distinguish which one is which. So, from the graph here, you can tell. If you try to focus on the CO double bond, so you see spectrum A does have a sharp peak at 1700. Same for spectrum B, okay, a very sharp peak at 1700. But do we have a sharp peak at 1700 for spectrum C? No, right? So you see here, we have no sharp peak at spectrum C. So you can tell there is no CO double bond. So this one has to be ethanol. This one has to be ethanol. Okay? Alright? Then, moving up to A and B here. So, you see, we're looking at the OH. You realize that for spectrum B, there is a broad peak. However, in spectrum A, we do not have a broad peak over here. Right? So, the absence of a broad peak at around 3000 cm negative 1 has to be the ethanol. So this one will be the ethanol. Okay? And this one will obviously be the ethanoic acid. So this is how we deduce. But for the reasoning, so how do we put down the reason for that. So now this one is very important, guys. Of course, if we see the presence of a peak, you can tell the presence of a bond or the functional group. But there is one more very important technique, is that if we cannot find a peak at a particular region, range, wave number, it is also providing a very valuable information regarding the structure, right? And just now, I just used the absence of a peak to make our deduction. So, for example, we can put down here, okay? You can say the absence of a broad peak, okay, at the 3000 cm minus here of spectrum A suggests the absence of OH bond, okay? So you see, this is how we make the assignment using the absence of a peak, okay? So this one is important. So with the absence of OH, which corresponds to ethanol, okay? So this one is to show you how we use the absence of a peak to make the assignment. So of course, actually there are many ways to do the assignment. You can also say, okay, the presence of both, okay, a sharp peak at 1700 and a broad peak at 3000 cm to the power negative 1, okay, suggest the presence of both C double bond O and OH respectively, okay, which corresponds to ethanol exit, okay? So here in spectrum B, okay? All right. Okay, so this one is to show you, okay, two ways of making the assignment, and there are, to be honest, many other ways to do the assignment. And because we are trying to sort out 3 items for 3 spectrum, so in our reasoning, I think all we have to do is to put down two assignment in order to sort them out. Of course, you can also put down another sentence saying that the presence of a sharp peak, the presence of a broad peak at 3000 cm to the power negative 1 suggests the presence of OH, but the absence of sharp peak at the range 1700 suggests the absence of a CO double bond, which corresponds to ethanol. You can put down another statement on that, okay? But in this case, two statements will be enough. Now, of course, you should tell me which one is which, okay? So C for ethanol, B for ethanol exit, and A for ethanol, okay? So that's it for the infrared. To be honest, for this kind of spectrum or spectroscopic technique, you do not need to understand a lot of concepts, right? You realize that you don't need to understand what is going on. All you have to know is how to apply, how to interpret the spectrum, and how you make assignment or deduction. Okay? So that means you need more practice. The more practice you have, then you will be more feeling comfortable with the spectrum. You will require lesser and lesser time to extract all the information from the spectrum. So more practice is crucial. Okay, so that's it for the video. I'll see you guys later. Bye bye.